Okay, hello and good morning. Let's take a look at what we've got. So we will continue on, talk about neural networks. We introduced neural networks last week, and we had forward feed, a neural network, and this is kind of the diagram of our network so far. We have 2 nodes in the input layer, 3 nodes in our hidden layer, 1 node in the output layer. We have a weight matrix that will contain all of the weights for the 6 connections between our input layer and the hidden layer. We have another weight matrix that has all of the weights for all the connections between our hidden layer and our output layer. This example that we're working through in class does not include bias terms, but we also showed how bias terms would factor in, and we'll work through some calculations and stuff for derivatives for our thing, and I leave it to a future homework assignment where you do it with same thing but with bias terms. Okay, so our weight matrices contain the weights for the connections between the different layers. And we have an activation function that gets applied after we multiply our kind of values in one node by our weight matrix to get the values in the next layer. And the activation function can really be any kind of function. It could be the identity function and you don't modify the value at all. Here we're applying the sigmoid activation function, or also called the logistic function. More popular today is the rectified linear unit, but the sigmoid function has historical popularity, and so we'll use that through our example today. And this is what forward propagation looks like. We take our values in our input matrix X multiplied by our first weight matrix W. That gives us our values in our hidden layer. We apply the activation function to the values in our hidden layer one at a time, or every single value. We don't change the dimensions there. We take those activated values, multiply it by our second weight matrix to get values in our output layer, of which there is only 1 node, so just 1 column of values. And then we apply the activation function. Could be the same or a different one. In our case, it's the same activation function to get our predicted values. So this is what we have. What we want to do now is we want to figure out what values should we put in to W1 and W2 so that our predicted values y hat are as close to the actual values of y. Okay, so we want to minimize the distance between the actual values of y and our predicted values of y hat, and the only things we can really change are the values inside our W matrices, okay? Because we're going to treat the incoming data X as fixed, we're going to treat the output values Y as fixed, and so, what we're trying to do is we're trying to change our Y hats, and the only things we can really control are the values that go inside W. So how are we going to do that? We are going to use gradient descent on our loss function. The loss function is going to measure the distance between the actual values and our predicted values, okay? And we want to find the values of W that will get our y hat values to be as close to the actual values as possible. And so we want to figure out what W's go in here so that we get this, and then and this will be as close as possible, okay? We're taking, this is our original loss function. We're going to modify it just ever so slightly by just changing this constant 1 over n to a constant 1 over 2. We're just going to multiply by this constant n over 2. And that just simplifies, that just cut, like when we take the derivative and stuff, this is something squared, and we'll just cancel this out. So it just gets rid of some constants, just so that our notation is a little bit cleaner to work with in the future. But it's effectively, if we figure out what values of W that minimize this, it's going to be the same values of W that minimize our loss function. Okay, So this process of figuring out the gradient of W, or the gradient of our loss function with respect to W1 or W2, that process is known as backpropagation. We are going to take kind of a traditional calculus approach to this problem of backpropagation, and you'll see kind of how it kind of works. In modern neural network things, they use a different algorithm for figuring out kind of the gradients of W1 and W2. It's just a different backpropagation algorithm. They don't kind of follow this calculus path. It's just because you'll see it gets kind of hairy as it is with just a very kind of simple network design. And so, our modern neural networks that have, hundreds of these hidden layers, they kind of, they do like this numeric process of seeing how one layer changes relative to the prior layer, and those changes, again, I guess, propagate backwards. And so that's the back propagation there. But effectively, I guess from like an analytic standpoint, we're effectively calculating the gradient or the derivative. And if you think back to calculus and think about derivatives, you have the chain rule where you have, if you have a function on a function, okay, you're going to basically take the derivative, and then you'll have like the chain rule where you take, you're basically multiplying all of these different derivatives. How does this change with respect to this, and how does that thing change with respect to something else, and how does that next thing change with respect to something else? And so you just kind of keep applying chain rule, and that effectively is backpropagation. Backpropagation is kind of like, how does this change with respect to this, and how did this thing change with respect to the thing prior to it, and how did that thing change with respect to the thing prior to that? So we are going to kind of do this backpropagation process kind of with this traditional, let's take derivatives or gradients, vector-based gradients here. There's also another note. We will do things in kind of matrix notation and stuff, but again, we are going to do some operations that are not strictly from linear algebra. So if you want to take, I want to take one matrix and I want to multiply by another matrix, but I want to do element-wise multiplication. That's not something we normally do in regular old linear algebra. But by using matrices, it gives us a convenient notation for saying, we have a bunch of values and they're arranged in this kind of grid format. And so, if you think about it, each of those values is just really like you're multiplying one number with another number, adding it to something else, and things like that. Okay, what did I write on this side? I wrote, training the network, means finding the set of weights to put in our weight matrices W1 and W2, so that, this function, this network, is going to make good predictions. We find the weights that are going to minimize the loss function. To minimize the loss function, we use gradient descent. So again, gradient descent is a way to help us find the minimum. So the traditional process to find the minimum is you take the gradient, you set it equal to 0, and you solve for where that gradient is equal to 0. What we're going to do here is we're going to go through the process of finding the gradient, but we'll see that it's going to be quite difficult to just take the resulting gradient, set it equal to 0, and solve. Okay? So instead of trying to solve for where that gradient is equal to 0, we will use the gradient as part of gradient descent, where we apply it iteratively. And so if you remember the gradient descent algorithm, you just imagine you have this contour space, and in our case, it's going to look kind of like a bowl, and you start off in one location, the gradient points upwards, and you take a step backwards, and so that just points downhill, okay? we saw gradient descent applied to linear regression, where we just had two parameters to adjust, the slope and the intercept, and that kind of created this bowl surface that we can do. It's the same kind of idea here, except now we're in, I guess, 10-dimensional hyperspace. Okay, we have 9 parameters that we can adjust. You know, here they are. We have 9 parameters that we can adjust, and so we're in this high dimensional space. But again, you just kind of have to imagine, you know, the idea of like having this contoured bowl, and you locate it at one direction. It's going to give you this basically 10-dimensional vector, and we take a step backwards, and that points downhill. Okay, so the same issues that exist with gradient descent earlier still exist here. Like, you're not guaranteed to converge. If your step size is too big, you can overshoot, and you have this kind of jumping backwards and forth thing. If you have a funny shaped response surface, okay, gradient descent doesn't necessarily converge to the optimum. Here, because our loss function is just y minus y hat squared, that keeps things fairly simple, so our thing works pretty well, but you can certainly have much more complicated things that get hard. Okay, all right, so anyway, here's our neural network, and what we want to do, what we want to end up with is these, we want to end up with our gradients. Okay, and so W1, the matrix W1 is a 2x3 matrix, and so the gradient, the resulting gradient, is going to be a matrix of partial derivatives, and it's going to be a 2x3 matrix consisting of, you know, the partial derivative of our loss function with respect to W11, partial derivative of our loss function with respect to W12, so on and so forth, for all 6 terms in W. And then our W2 matrix has 3 terms in it, and we're going to find the gradient, which is going to also have be a matrix of partial derivatives. We have 3 terms in W2, so we'll have 3 terms in our gradient with respect to W2. Okay, and if we had bias terms, we would have gradients with respect to our bias matrices. Okay, and that's for your homework. Okay, so we are going to do back propagation. We're going to start by, because we're going to work backwards. So starting with our output, kind of the first thing before that is our W2 matrix. Then we have our hidden layer, and then we have a W1 matrix. So we're going to find, working backwards, we're going to find the gradient of the loss function with respect to our second weight matrix. And so our loss function is the difference between each observation and the predicted value, and we'll take that difference when we're going to square it. Okay, we have n of these observations, so we'll do this n times, we'll square them all and add them all up. Okay, and so the derivative of a sum is the same as the sum of the derivatives, so I'll bring this in here. And so here I'm going to have y minus y hat squared, and then I can, when I take the derivative of this, the 2 comes down, it cancels that out. And because of the chain rule here, okay, we ask, well, what changes with respect to W2? So y is a constant. This is part of our data. Okay, we're going to treat our data as fixed. So y does not change with respect to W2. But y hat, these are our predictions, that will change if I change W2. So if I change any of the values in my W2 matrix, that will have an effect on y hat. And so therefore, when I apply kind of chain rule here, I'm going to get the sum of y minus y hat times -1 applied here, and then we will have the derivative now of y hat as it changes with respect to W2. Okay, and so now I'm going to further split this, all right, and I'm going to say, okay, how do we go from W2 to y hat? Okay, well, basically we have these values, okay, there's an intermediate value, Zn, okay, where what we've done is we've taken kind of the outputs of our activation layer, or we take our activated values in the hidden layer, multiply it by W2. That gives me Z, and then I apply an activation function to Z to get my Y hat. So I'm going to say, well, how does Y hat change with respect to that intermediate value Z? And then we can ask, how does Z change with respect to any changes in my W2 matrix? Okay, and here we're just looking at kind of like the nth observation, and we're going to say, we'll do this for the first observation, and then we would do it for the second observation, and whatever all of these things are, we would add them all up to get our kind of our total, I guess, gradient, or how everything changes there. Okay, so what we have is that we have our kind of our intermediate value, and then we apply the activation function to this to get our prediction value Y hat. And so I can say, well, what's the derivative, of Y hat sub n with respect to, Z sub n, okay? And we're going to just say, well, we can just call this f prime, okay? This is basically the derivative of our activation function. And then we can ask, okay, well, what is f prime then? Okay, well, our activation function is 1 over 1 plus e to the negative t, or whatever value we plug in here. In this case, it would be zn3. What is the derivative of that? So we can apply quotient rule. We can say f is u over v, and u is 1, and v is 1 plus e to the negative t, okay? So, quotient rule is u prime v minus uv prime over v squared, and so if you apply all of that, f prime of zn3 is going to be e to the negative zn3 divided by 1 plus e to the negative zn3 quantity squared. This would be what we have. Okay, this is our f prime. Now, just to kind of keep things clean, I'm going to just leave it at f prime zn3. Okay, so I'm going to just replace this part with this. Okay, so this is my gradient so far. How does the loss function change with respect to changes in W2? Well, we'll take the difference between the actual value and any of our predicted values, multiply it by f prime of this, and then we'll say, how does zn3 change with respect to W2? So we have the partial of this. Okay, is that okay so far? All right, and then so now we can ask, okay, well, how does this, what's this part? Okay, well, this part, if we think about how do we get our Z matrix is the result of multiplying our activated values in the hidden layer times W2, right? So in our diagram, so this is our hidden layer, and we go from Zn1, or is it Zn2? I forget, whatever. But basically, these after we apply the activation function, we get our activated values, okay? And then we have our W2 values here. This is W1, W2. So we have that, and then we have our activation values there, okay? And so if we just think about like the nth observation, the nth observation would be our nth activated value times our W2 matrix, okay? The nth activated set, for the nth observation, you would have 3 values in that activation layer. So we have 3 values, so 1 by 3 by 3 by 1, that's going to give us 1 value here. So if we just look at one value here, we can say, okay, what is the gradient of this, okay, with respect to changes in W, right? So this is just using our kind of our gradient rules. So if you remember, where did my useful gradient relations go? say it's from our very first lecture, maybe. So we have useful gradient relations here. And so if you have basically x times x transpose w, it would be x, okay? And here we have a times w, so it would be the transpose of a, okay? So this is what we have. We're going to say, okay, how does this change with respect to this? So we're going to get a transpose. And the gradient of this is going to be 3 by 1, and we have a sub n transpose, okay? So that's what we have. We'll replace this with a sub n transpose. And there is our answer, okay? So this is, how does our loss function change with respect to W2? We're going to say it's y minus y hat times f prime of zn times a sub n transpose. Okay, now this thing is 3 by 1, okay? And a sub n is 1 by 3. A sub n transpose is going to be 3 by 1. All of these values, these are scalar values. Okay, y sub n is a scalar value, y hat sub n is a scalar value, z at the third layer is a scalar value. So this is all just one thing. And we have a summation sign, and so we might say, well, can we, so we could do this for our first observation, calculate this value, and then we do it for our second observation, and third observation, we add them all together. We could have like a big for loop and say, you know, calculate this for the first value, then, you know, calculate it for the second value and add it to the previous thing. And you can have a for loop and it would calculate it, right? But, you know, from a computational perspective, for loops are slow, okay? So can we find like a vectorized solution to speed things up? And yes, we can, okay? So if I kind of replace not just the replace this with the nth observation, just one observation out of many, I can just take the entire vector of y, okay, and I've got n of those values, right? And instead of just looking at the nth prediction of y, the nth y hat value, I can take the entire vector of y hat values, and I can do y minus y hat, and then I will have basically an entire vector of length n of residuals. Okay, that's fine. What about the nth observation in z? Okay, well that's just one. I can replace it with the entire vector of z values, and that I would have n of those things. Okay, now if we think about the nth observation, like the first observation here, I'm taking the first value minus the first value, whatever this thing is. So the first residual times the first value here, okay? And then I would want to also do this for the second value, right? I would have the second data value, the second prediction, I have the second residual times the second value, okay? So if I just replace these directly with the vectors, what I want to do here is I want to do element-wise multiplication, right? So I want to take all n values in this vector and multiply the first one with the first one, and the second one with the second one, and the third one with the third one, okay? So here, what I want to do is I'm going to want to do element-wise multiplication between this vector and this vector. Does that kind of make sense? Right? So again, we're borrowing like matrix notation in linear algebra, but we're not doing strict linear algebra business. We're going to want to do like element-wise multiplication, okay? Also, over here, if I think about like what is this? So we have activated values. I've got 3 activated values for each observation, okay? So for the first one, I just have 3 values, okay? But then I've got n observations, so I'm going to have a big matrix of that's 3 by n, okay? And if I just replace the nth observation in matrix, the nth row in matrix A with the full matrix A, okay, this whole thing is 3 by n. And I can't just do matrix multiplication here because none of our dimensions line up, right? So I can say, well, you know, what does this kind of look like? So again, if we just focus on one value, this is a scalar value, this is a scalar value, this is a 3 by 1, and in this case, I can just kind of rearrange my terms. I can just kind of take this 3 by 1, bring it up front, multiply it by a scalar, and multiply it by a scalar, and I would still have a 3 by 1 times a 1 by 1. I haven't really changed anything here, okay? In regular linear algebra, you can't just take matrices and move them around and just say, hey, I want to do this, okay? Again, we're not doing strict linear algebra. We are borrowing the notation of matrices, but we're thinking individually. What's going on is, like, for this nth observation, I have a number here and a number here and a number here that I'm multiplying together, okay? Here I've got 3 numbers here. It's being multiplied by the residual, which is a scalar. It's multiplying by basically my pre-value before I apply an activation function here, okay? And then now that I've kind of rearranged my terms, I can say, okay, well, let's go back and use the entire matrix with n rows, okay? So the entire A matrix is 3 by n, okay? I have the entire vector of residuals, which is n by 1. I've got the entire vector of basically z3 values, which is n by 1. And I want to, do it first value times the first value, second value times the second value. So, here's just kind of this stand-in symbol to indicate we have element-wise multiplication. Okay, so I'm going to have this circle dot to indicate I'm doing element-wise multiplication between this and this. So this result is going to be n by 1, and I can multiply that by a, which is 3 by n. And if I do that, this is effectively doing basically the 3 values times this, and then for each row n, doing it for the first row, then the second row, and the third row. And then when you do it using the matrix notation, the summation is included there, right? So when you do a 3 by n times an n by 1, you're going to do it for the first row, and the second row, and the third row, and then they all get added up together because of matrix multiplication. The summation is implicit. So I don't have to have a for loop, okay? I don't have to have a for loop and say do it for 1 and then 2 and then 3 and so on. I can just do matrix operations, and I can just take the A matrix and multiply it by this vector, and which gets element multiplied by this vector, okay? And so this is going to give us a computation that we can put into the computer that will be quick, okay? Again, I didn't have to do this. I could have left it in this form with the summation sign, okay? And a summation sign in computer notation is basically a for loop, okay? I could have left it that way, but again, for loops on computers are, computationally slow. I mean, unless you have like a compiled software like C, where it looks for all of these computational shortcuts and stuff like that. But in general, for loops, especially in R, an interpreted language, it's going to be slow. So if we can vectorize things, much better. So we're going to go from the summation and we vectorize it, okay, into this form. All right, so this is my my result here, okay, for what is the loss function, the gradient of the loss function with respect to our second weight matrix. All right. Does that feel okay? All right, so we're going to do the same thing. Now we want to find the gradient of the loss function with respect to our changes in our first weight matrix. Okay, so we have the outputs. These are going to be our y hats. Well, this gives me, I guess, z, and then we apply the activation function. This gives me my y hats, right? So we're going to find how does it change with respect to W1. okay? So in the beginning, it kind of follows all of the same steps. We want to know, okay, how does, it change to respect to W1, and really only Y hat changes when you make changes to W1. So we'll say, okay, how does Y hat change with respect to Z? And then we already did that part, and that's F prime of Z. Now we have to say, okay, well, how does the Z value change with respect to W1, okay? So we're going to say, okay, well, how does Z change with respect to our activated values A? And then how do our activated values change with respect to W1, okay? So the values Z here are the result of taking our activated values multiplied by our second weight matrix, okay? So now we want to know, okay, how does Z change with respect to changes in A, okay? And so, again, using our gradient relation, we have basically an A times W. So how does this change with respect to A? We're going to basically get W transpose, okay? So this is what we have here. So W is a 3x1 matrix. W2 transpose is going to be a 1x3. So I'm going to bring that over here, okay? So here I have, so if we're looking at the nth observation, we have a scalar value here, a scalar value here. W2 transpose is going to be 1/3, okay? And so this scalar value is going to get multiplied by all three values in W2 transpose, and we want to know, okay, how do our activated values here change with respect to W1? And so those activated values are the result of applying a function to Z, the Z values coming in here. And then the Z values change when we multiply basically the input values X times W1, okay? So this part, because we have the same activation function in the hidden layer, this part is A2 is just going to be F prime applied to the values in our hidden layer here, okay? So it's kind of like the same logic that it gets applied here. All right, so if we think about this, okay, the values inside the nth row of A, okay, we have, it's one row with three values, okay? So this matrix here, or this, I guess, the nth row in Z is going to be, one row with three values in it, okay? So far, this is what we have. We've got, a scalar value. This is 1/3. This is also 1/3, okay? And so we're going to want to do element-wise multiplication between each element in this part with each element in this part. If we think about, like, what are the values inside here and what are the values inside here, what's being done here. Okay, this last bit feels the weirdest because now if we think about the nth row in Z, okay, the nth row in Z is basically one row with three values, okay? How did we get that one row with three values? We got that by taking the nth row in X, okay, and X is a matrix with n rows and 2 columns, so basically the nth row is 1/2, and we multiplied that by our first weight matrix, which has 6 values arranged 2/3, okay, and when you do a 1/2 times a 2/3, you get this result of a 1/3. So this next part says, okay, well, what is the derivative of this with respect to changes in W? Okay, how does this change with respect to changes in W? So if we think about, what's happening when we get basically our values in Z, we have 3 values, right? We have one row and we have 3 values. First value, second value, third value, okay? And here we have the nth row in X, so I've got two values here, 1 by 2, and then I have this 2 by 3 matrix. So if I do this time, this row times this first column, I'll get xn1 w11 plus xn2 times w21. And then for the value in the second column, it's basically this times the second column. And then the third column here is basically that row times this. So if we think about, like, if I add a tiny little element to, let's say, any value in this top row, okay, then how is it going to affect the output here? Basically, it's going to be, whatever I add here gets multiplied by xn1. Whatever I add here will get multiplied by xn1. Okay, well, anything I add to this bottom row will get multiplied by xn2. Okay, so if I add some element epsilon, the result is going to be xn1 times, the ending matrix is going to have a result of xn1 times epsilon or something like that. So we can kind of think of the partial derivative of Zn2 being a 2 by 1 matrix, basically the transpose of our x. Okay, so we're going to say, how does the nth row in Z change with respect to W1? We're going to get the nth row in X transpose. So this is what we have here. So all of this, so if I kind of plug that in to back here, okay, or right here, this is what we have. Now all of our dimensions are all misaligned, and if you, again, focus on each of the elements that we're getting, okay? So the result, remember, we want to find, like, the gradient of J with respect to our W1 matrix. And so we know this result should be a 2 by 3 matrix, because it should be like this matrix of partials, okay? W1 has dimensions 2 by 3, and so the matrix of partials should also have dimension 2 by 3. So we do want 2 rows, we do want 3 columns, and we think about, okay, what is the element that's going to go in the top left corner? It's going to be the partial derivative with respect to that top left element in W. And if you look at all of the kind of individual values that get multiplied together, we can show that it's going to be basically the first value in X and the first value in W2 and Zn3, right? And then if you want to look at, like, the second row, it'll be like the second value in X times that. And if you look at the bottom right corner, second row, third column, it'll be the second row in X, and the third column over here, okay, is going to be the relationship. So as far as for each observation, we're going to take our nth observation in X transpose. That's going to be 2 by 1. All of these are scalar values. Our W2 matrix is 1 by 3, or 3 by 1, and so we'll take the transpose of that. We have element-wise multiplication between that and each of the elements in our second Z matrix here, okay? And right now we have a summation. So we could leave it in this form and just say, hey, do it for the first row, do it for the second row, do it for the third row, and then do a for loop and add them all up. Ideally, we would like to get rid of the summation sign and put everything into kind of matrix or vector notation so we can kind of speed things up computationally. So we'll do that, okay? So I'm going to replace X sub n, the nth row in X, with the entire X matrix. And if I do that, the entire X matrix is going to be 2 by n, okay? If I replace y minus y hat, I'll get the kind of the entire vector of residuals. Over here, I will have the entire kind of vector of output values before I activate them. Here I've got my second weight matrix, which is 1 by 3, okay? There's no n there. And then here I have the entire matrix of kind of activated values in the middle here, okay? Or not activated values, I guess values prior to their activation, okay? Which is going to be n rows, 3 columns. So this whole thing in the middle will multiply out to be n by 3. This whole matrix over here is n by 3. And again, if you think about each kind of individual value in the thing, we want the top left value multiplied by the top left value. We want the second value on the left multiplied by the second value on the left. So we're going to have element-wise multiplication between this entire thing and this entire thing. So this entire thing right here is going to be n by 3. Because I've got an n by 3 here. Element multiplies by this, which is n by 3. And so this entire thing right here is going to be n by 3. Okay? And so, I don't know, maybe you can see how writing dimensions underneath all of these things is helpful as far as kind of just making sure we're doing things correctly. Because if it's just letters, you're just like, oh yeah, everything should be multiplied. And then when you try to put it into the computer, it like blows up. It says, what is it? Non-conformable dimensions or something. But so this is all n by 3. X, the entire matrix of X is going to be n by 2, and we have X transpose, so 2 by n. And so when you do this whole thing, then it becomes a 2 by 3. And that's what we have. Okay. So, so we'll go ahead and punch this into the computer. Okay, so I've got this result is 2 by 3, and that's what we want. Okay, so coding it up. So this is, I think, the great part about R is it's relatively easy to go directly from something in kind of this matrix form into R code, just because R looks a lot like matrix operations here. So we're going to just kind of code this in there. So as far as the activation function, this is just a function 1 over 1 plus e to the negative t. So if I just gave you an assignment, write a function in R that that does this function, this would be very easy. You would just say, okay, 1 over 1 plus e to the negative. Here I put in z, but you could have put in t or whatever, and this is what we have. All right, no mystery here, right? This is a very straightforward function. Okay, let's get our data in. Okay, so the data, that was on a different slide. Right here. Pull this up. All right, so my silly example was, okay, we have 3 observations in X, 3, 5, 10, 5, 1, 2, and then 75, 82, 93. So we're going to put that into our matrix. I have a matrix X, 3, 5, 10, 5, 1, 2, and then matrix Y, 75, 82, 93. Now, because of the sigmoid activation function, it really likes values between, say, like -3 and +3. And once you get values outside of that, basically, you're either going to get 1 or 0 or, something very, very, very close to 1 or something very, very, very close to 0. So just to kind of put things on a reasonable scale, I'm going to take my value 75, 82, 93, I'm going to divide by 100, so I get 0.75, 0.82, 0.93. I can do something similar over here, but here I just divide by the column max, which over here is going to give me 3 divided by 10, so I get 0.3, 0.5, and 1, and then I'll divide by the column max over here, so this will be 1, the second row will be 0.2, and this third row will be 0.4. Okay, so that's all. Okay, and then here I just have placeholders, so it can be adapted. We're going to say our input layer has 2 nodes, output layer has 1 node, hidden layer has 3 nodes, and this just will give me some flexibility in case I want to go from hidden layer 3 nodes to hidden layer 20 nodes or something like that. Okay, and so as far as forward feed, we do x times w1 and apply this. So if I wanted to do this, it's just a direct translation. So here I'm just going to create an arbitrary matrix. This I'm just filling it with 1s. Obviously these are not going to be good values to have, but I'm just start off with ones. W1 is going to be a 2 by 3 matrix of ones. W2 is going to be a 2 by 3 matrix of ones. And then so if I want to do forward feed and do x times W1, I just do x matrix multiply by W1, that'll give me Z2. I'll apply the sigmoid function to Z2, that's going to give me matrix A2. Then I'll do A2 matrix multiply by W2, that'll give me Z3. Sigmoid applied to Z3, and that'll give me Y hat. And you can see that's just a direct translation of our forward feed stuff there. Okay, so actually let me, I have this all coded up. This is available in the modules under neural network example code right here. So you can download the script if you want. And let me just kind of put this in here so you can see after, so there's X, and if this is the raw values, and after I kind of scale them, you can see we go from 3, 5, 10 to 0.3, 0.51, and then 5, 1, 2 becomes 1, 0.2, and 0.4, and then my Y values will be scaled down to 0.75, 0.82, 0.93, 213, W. Okay, so you can see all I'm doing is I'm just multiplying, right? So X times W1 gives me Z2, and you can see the dimensions. So Z2 is going to be n by 3, and then Z3 is n by 1, and then Y hat is going to be n by 1. 3 rows. So right now, my W1 matrix is all ones, and so these are we have these the actual values of Y are that, and right now my predictions of Y hat are no good. Okay, I've got 0.9135, 0.88, and 0.917, and ideally we want 0.75, 0.82, and 0.93. So these are not good estimates right now. Okay, but we will do gradient descent to try to figure out some good values of W1 and W2. Okay, so we have our cost function, which is going to be Y minus Y hat squared, and we'll take the sum of everything, and we'll calculate our current cost. So right now our current cost, between Y and Y hat is 0.0153. Okay, it's the difference between 0.75 and 0.913 and 0.82 and 0.88 and whatever. Okay, that's our current cost. And we have our sigmoid prime, our f prime, which is e to the negative z. This is just from one of the other slides. Okay. And then we have the gradients, right? So we went through all of the work and we said our gradient is going to be A2 transpose times negative of Y minus Y hat times Z3, F prime Z3, and then and that's what we have here, okay? And so here I'm going to call this part delta 3. I got Y minus Y hat, element multiply, and so in R, element wise multiplication when you have two vectors is going to be just the star, and so I'll have that multiplied by F prime Z3, and so that works out right there. Okay, so like Z underscore 3 is 3 by 1, and I can apply sigmoid prime to Z3, and that's also going to be 3 by 1. Okay, and then Y minus Y hat is 3 by 1, and so I can do element multiplication between this and this. Right? So delta 3 is going to be 3 by 1, okay? And then I can, A2 is 3 by 3, and so if I multiply this by this, the result is going to be 3 by 1. Okay, so that's what I have. And then, so this is just a direct going from kind of the work that we did on the previous slides and their back propagation slides to what we have here, okay? And then getting the gradient with respect to W1, I just go directly also. I have all of this, x2 transpose times this times W2 transpose element multiplied by f prime z3. This part is this, so I'm going to call all of this delta 2, which is going to be delta 2 times W2 transpose element wise multiply f prime z2. So this is just, I'm just going straight to what I have. W2 transpose is W2 wrapped in T. So this is W2 transpose. This is matrix multiply here. And this is element-wise multiplication with sigmoid prime Z2. So that's going to give me delta 2. And then to get my dj dw1 here, that's going to be X transpose matrix multiply delta 2. So I'm just taking the work that we did mathematically and getting exactly what we worked out, back on these slides. So I'm just going straight from what we have here into using R's matrix notation and going directly into this. Okay, so that's what we have. These are just our current kind of resulting gradients, and what we do is we will take our current values of W1, which are currently just all number ones, okay? And this is my gradient, so I'm going to just take my current value of W and then take a step backwards from the gradient. So the gradient points in the direction uphill, we take a step backwards. So I'm going to just do W1 minus, this is an arbitrary scalar value, and just do W1 minus scalar times dj dw1, right? And so when I do that, my W's, which used to just all be ones, is now something a little bit different, okay? I do the same thing with W2s. And so my W2s, which used to be all ones as well, is now a slightly different set of values. And we can update again, all right? And so the question is, what are, did our costs improve, okay? So our old y-hat values, when everything was just number ones, these were our predictions. And we want to say, okay, now that I've recomputed my W1 and W2 values, okay, do my predictions get better? Okay, so I'll just take X, I've got a new W1 value, and I'll do forward feed. So X times W1, sigmoid applied to that, those activated values times W2, and then a sigmoid applied to that. So these are my new predicted values. So my previous predicted values were that, and my new predicted values are this. Are these any better? Okay, the actual values of y are this. So we went from 0.913 down to 0.89. The true value is 0.75, so that does seem better. We went from 0.88 down to 0.86, and the true value is 0.82, so that does seem better. And we went from 0.917 to 0.903, and the true value is 0.93. So this one didn't get that much better. This actually went in the wrong direction, but we got closer for the first two, went in the wrong direction for the third one, but we'll evaluate from there. And so we can calculate what is the cost here. So the initial, our first cost function, this was the amount of error that we had. And our second cost, our amount of error went down. So that's a good sign, okay? I have this whole section on numeric gradient checking. I'm gonna skip over that, okay? But what we'll do is we'll go ahead and do gradient descent. So I'm gonna just start off, I'm gonna start from the beginning. This time, rather than just populating W1 and W2 with all ones, I'm gonna just populate W1 and W2 with random values, okay? So W1 and W2, they're random values. They're just kind of all over the place. And I'm going to just run a loop, okay? And this loop looks like this, okay? And So all we do is we just take our current values of W1 and W2. We do the forward feed. X times W1, it gives me Z2. Sigmoid applied to that gives me A2. A2 times W2 gives me Z3. Sigmoid applied to that gives me Y hat. So these are my current predicted values, Y hat. Okay. This is not necessary, but just to kind of show how our cost has improved, I'm going to calculate the value of the loss function, the cost between Y and Y hat. Okay, and we're going to store that in cost history. Okay, but really we just need Y hat because that factors into our calculations of our gradients. So the gradient is found by doing Y minus Y hat times sigmoid prime Z3 times A2 transpose. Okay, and then dj dw1 is x transpose times all of this. Okay, and so this will give me calculations of my gradients, dj dw2 and dj dw1. These are the gradients. How does the loss function change with that? Okay, and then this is gradient descent. You take your current value of w1 and subtract off some scalar times your gradient. You take your current value of w2 and subtract off the scalar times the gradient. So as far as the code goes, I think it's relatively simple and straightforward, okay? You have to take your current values of W1 and W2 to get what is your current predicted values. The current predicted values are used to figure out what your gradients are, okay? Because you want to know how far are my predicted values away from the actual values, and therefore, like, the direction we need to head is in this direction to kind of either, to improve things. And so you figure that will give you the gradient between, that you do. And then once you have your gradient, you just update your current values of W1 and W2. You just subtract off some value of the gradient. So that is our loop, okay? And so I'm going to just run this. I'm going to let it run for 10,000 iterations. And it's done, okay? It's a matrix operation, so it works quickly. It's done 10,000 iterations. Okay, so this is the resulting matrix of weights. W1 has these values, and W2 has these values. These values are meaningless. Again, with neural networks, we have no real interpretability of what the resulting weights of our nodes are, okay? We don't know. But what we will do is we're going to look at our predictions. So my Y hat values are this, and the actual values of Y are this, right? So the actual values were 0.75, 0.82, and 0.93, and after 10,000 iterations, I got 0.749998, and 0.82005, and 0.92989, okay? So I say, okay, what is the cost there? It's pretty small. It's on the order of 10 to the minus 9, okay? I can see, well, how did cost improve over time, okay? In the beginning, we had some kind of cost, and we can see our cost rapidly dropped, and then kind of leveled off, and then we found some location and improved things, and now it's kind of flat, okay? We can plot a log cost on a log scale, and we can see, okay, dramatic improvement, kind of slowed down for a bit, and then now we've got to some basically incremental, like when you see a straight line in a log plot, it basically means like with each iteration you're just improving by some scale. So it's kind of like at the next iteration your errors you shrink by half, and then at the next iteration it's a half of that, and at the next iteration it's a half of that or something. So you're just kind of it's improving at I guess a geometric rate is what this is. Okay, and there you go. That's gradient descent applied to our neural network. I think all this to show there were no, as far as like the process we use to train our neural network, there's like no magic here, right? This is we're doing matrix operations and we're just multiplying things together versus and so my hope is this gives you some insight as far as like how does a neural network work and what's happening on the inside versus like, in production you wouldn't use this. In production you'd probably use like Keras tensor, which is built off of TensorFlow, and there's all kinds of like stuff optimized and it works very kind of efficiently, okay? But at its heart, what is happening, we're just multiplying matrices, or I guess higher dimensional things, tensors together and stuff like that. Yeah, question?
Do you have any intuition why the loss gets stuck between that like 1 and 2,000?
Oh, like why it gets flat here?
Yeah.
Intuition, no, I don't really know. So there's a couple things. We only have 3 observations here. This is this might have been at some location where the parameters are just like they're not great parameters, and depending on this happens a lot with the logistic or sigmoid function and this is why we don't like the sigmoid function anymore, is that your prediction could have ended up in a zone where like the slope is really flat, like because it's asymptotic at high ends and at the low ends. So your slope could have been flat. And so you just don't get a whole lot of information as far as like, am I going downhill? Because you can't really tell, is it downhill because it's like so flat, right? And so sometimes you get stuck in these kind of flattish zones and it's hard to know, but sometimes you let it run long enough and it's like, oh, we did find some improvement and things like that. So that's that. Oh, I'm the worst. I forget about. Okay.